Welcome. In our previous lesson on momentum, we discovered momentum conservation and how it holds at a wide variety of levels, right, all the way from the level of galactic collisions down to the level of microscopic and subatomic collisions. We also discovered that kinetic energy and momentum behave differently in collisions. So we want to take a closer look at that difference and use the difference in kinetic energy behavior in different kinds of collisions to classify collisions. Let's get started. Let's clarify that for the sake of this discussion, we're going to assume that momentum is conserved in all collisions, okay? And let me tell you why we can make that assumption. Remember that every collision has a force time graph, like you see pictured here. Remember we discussed that typically these collisions, right, like a baseball with a bat, a golf ball with a club, right, that happens in a very short time period. In other words, this time right here, okay, is on the order of milliseconds. So over that period of time, right, even if in this collision here, okay, even in this collision there's friction and air resistance, for example, over the time of the collision, milliseconds, we can basically neglect those horizontal forces. We can assume that the unbalanced forces on the system during that small time of collision come to zero. Okay, so I want to clarify, okay, because there's a point of confusion. I want to clarify that for all collisions, right, the momentum is conserved. But the kinetic energy is not conserved. So we're going to compare the kinetic energy of the system before the collision to the kinetic energy after the collision. And that's how we're going to classify collisions. So over here on the right, you see that this is when kinetic energy is also conserved. There are some collisions in which kinetic energy is conserved. Those are called elastic collisions. Cars that bump together without touching, right, if they have magnetic bumpers, that would be an example. You've heard of a gravitational slingshot, which is how we use the gravitational energy of a planet to slingshot a satellite to another planet. That's how we got the satellites all the way out with the solar system, right? Those are examples of elastic collisions. Collisions where they don't actually touch. You're going to see most collisions in the universe, okay, fall in this broad middle category where kinetic energy is not conserved. We call those inelastic collisions. And then there's a class of inelastic collisions, okay, where the objects actually stick together after collision, right? And those would be called perfectly inelastic. There's no clear way in terms of the value of kinetic energy to determine perfectly inelastic from inelastic. In other words, perfect inelastic collisions don't always have a lot less kinetic energy at the end. But on the spectrum, it's meaningful to put it this way. Okay, so we have three different types of collisions. You actually might have a fourth type here, okay, which is not an official category, super elastic collisions, and that's where actually the kinetic energy at the end, okay, is greater than at the beginning. That's not an official category, but I can give you an example of that in class. All right, let's delve into collisions a little more closely, one at a time. We're going to look at perfectly inelastic collisions, okay, in which the objects stick together after the collision. We can actually derive a meaningful result, a new equation that doesn't show up on your formula chart, but that is useful. Okay, it's relating kinetic energy and momentum to each other. So we're going to take the kinetic energy equation. You see that we already know that they're similar in their terms, right? They both have that mv in them. So we want to come up with a new expression, okay, which is ke in terms of p. Okay. And what we're just going to do is we're going to substitute one into the other, okay? And when you do that, you're going to get this right here, Ke equals P squared over 2m. I'm not going to do all the math. You can look it up in the textbook if you'd like. But this is an equation that relates the kinetic energy to the momentum, okay? And we can use this equation to prove that in a perfectly inelastic collision, the final kinetic energy will always be less than the initial kinetic energy. We're going to look at this problem here. We're going to assume that in this case, the velocity of this second car, okay, initially is 0, right? And then afterwards they move together with some final velocity. So we can calculate the initial momentum, okay, in terms of, the initial kinetic energy in terms of the momentum. Initially, the only thing that's moving, I guess you should have M1 and M2. The only thing that's moving is M1, right? So this is going to be M1 V1I squared, right? Squared like that over the gist of the first one, right? Because the second one's not moving. Okay. So And then at the end, right, we can do the same thing again. We can really just simplify this as p squared over 2m1. Okay. Now after the collision, we know that momentum is conserved, so the momentum has to be the same at the top. But now we have two masses moving, right? And you can see that this turn, right, is definitely going to be less than the initial. In other words, the final kinetic energy is definitely less than the initial. Kinetic energy is lost in the collision. Now you should be able to explain where the kinetic energy goes. Okay. It goes into other kinds of energy, right? Because we know that at a global universal level, energy is conserved. So if kinetic energy is lost, doesn't mean it just disappeared, right? It went into other things. In every collision, you're going to have heat generated from the collision. Sound, typically, if they make contact. Okay, so sound and heat. And then sometimes if there's a permanent deformation, right, like a car wreck in which you get a dent, the energy would have changed the configuration of your car by putting a dent in it. So typically, kinetic energy, if it's lost, goes into sound, goes into heat, goes into deformation. All right, let's look at an example problem. This is probably the classic perfectly inelastic collision example problem. It's called the ballistic pendulum. Okay, it's a low-tech way of measuring the velocity of a high-speed object. What you do is you take a high-speed object like a bullet, okay, like you see here, and you shoot it into a block so that it completely embeds itself into the block. The block, as a result, will rise up. We want to calculate how high does the block rise, okay? And if we're able to measure that, right, in this case we're going to calculate it, but if we were able to measure it, then we could work backwards and solve for the velocity of the bullet, okay? So again, it's a low-tech way of getting a measurement of a high-speed object. We're going to use conservation of energy and conservation of momentum together. So the first thing we're going to do is we're going to apply conservation of momentum. Okay, so before the collision, all we have is the bullet moving. And then afterwards, the two move together as one object, right? It's a perfectly inelastic collision. Okay, and for the ballistic pendulum to work, you have to have the block's mass has to be much bigger than the bullet, right? So that's why I used capital M. And they're going to move together with one final velocity. Okay, so you can solve for that. It's just this expression here. So remember that during this collision, energy is not conserved, or mechanical energy is not conserved, right? Kinetic energy is not conserved. Momentum is conserved, kinetic energy is not. However, once the bullet has embedded itself into the block, there are no longer any non-conservative forces working, right? Only the conservative force of gravity. So now we can apply mechanical energy conservation. So we write that out. And assuming that the block, right, the level of the block is our zero level, okay, we have only kinetic energy at the beginning, right, and then when it reaches its highest point, okay, we only have potential energy. Now in this case, the M is the combined mass, right, so notice actually that the mass cancels out, okay. You'll see here that the height is simply v squared over 2g, right? Where that v will be the final velocity of the block, right? So we might write it this way, okay, like so. That would be the final velocity, that squared, right, times 1 over 2g. So that will be the height. So if we knew the height, right, and we knew the mass of the block and the mass of the bullet, then we could solve backwards and get the velocity of the block. Excuse me, the velocity of the bullet. So there you go, perfectly inelastic collisions in action. All right, let's take a closer look at elastic collisions. Okay, remember an example of an elastic collision would be a gravitational slingshot or a collision in which no contact actually takes place. Okay, for example, like I'll show you in class, two cars that have magnetic bumpers. So in elastic collisions, we say that kinetic energy is conserved. If you look at this example here, we have two cars approaching each other. And you can see what the kinetic energy conservation equation looks like. It's kind of messy, right? There's squares, and it's really not nearly as fun to work with as momentum. Now, you can cancel out the halves, right? You can multiply each term by 2. You can get rid of the halves, but you still got a bunch of squares to work with. It's kind of ugly. Fortunately, somebody ahead of us, right, blazed a trail, and they realized that you could reduce this equation to something a lot simpler. It's actually going to reduce to this right here, very simple. Okay, we're going to compare the final velocities, okay, to the initial velocity. And when kinetic energy is conserved, okay, it's going to look like this right here. Okay? Now, this right here, this term is called the velocity of recession. It's the speed at which the two objects recede from each other. Okay? And this term over here is called, as you might guess, the velocity of approach. With what speed do they approach each other? So in kinetic energy conservation and elastic collision, these two are equal to each other. Okay? Again, let's take a look at an example problem. All right, we have two objects. They're both moving in the same direction. M1 is heavier and faster, all right, and it's colliding with the car ahead of it. But we're going to assume that it's an elastic collision. We would like you to find the velocities of the two objects after the collision. Well, we can go ahead and start here with our momentum conservation. And let me pause and write that out. Okay, I shifted the work over to the other side of the screen. When you look at those numbers, when you look at the equation, you see that you have one equation but two unknowns. Okay, and that's where you're going to use the fact that this is an elastic collision. Okay, because if you have two unknowns, you need two equations. But remember that with an elastic collision, you have that additional equation, right? The kinetic energy equation. But remember, you get to use the easy version of it. Okay, not the complicated version of it. So let me pause again and write that out. Okay, so that looks like this right here. Now on the right side, we can solve for this, right? V2I was -2, and V1I was 3. Okay, so that their speed of approach is 5. I hope that makes sense to you, right? If you're going 3 and someone's coming at you with 2, it's like you're approaching each other with 5, speed of 5, right? If you're going 60 miles an hour, approaching a car coming at you 60 miles an hour, your relative velocity to each other is 120 miles an hour, and that's why it's so destructive. So in this case, this is 5, and so we can solve for 1 here in terms of the other, right? In other words, V2F is 5 plus V1F, and then we can come over here, okay, to our momentum equation, and here on the right side, we can solve, we're just going to plug in here our new expression. And now, I'm not going to finish this, I'll let you finish it on your own, but you can see now you have an expression that is in terms of one variable, right? So you can solve that on your own for V1F and then go back and solve it for V2F. We want to look at one last concept, okay, and that's the concept, it's called the coefficient of restitution. It's actually a slightly neater and niftier way to help us classify collisions. So let's take a look again at our kinetic energy conservation equation. Okay, right here. And we're going to use these terms, okay? We're going to use this. Remember, the one side is called, the left side is called the velocity of recession. The right side is called the velocity of approach. We're going to make a ratio out of these two. Okay? We're going to compare these two. Now, you know that when they're equal to each other, it's going to be equal to 1. So what we're going to do is just going to divide both sides. Okay? We're not going to worry about signs. We can take the absolute value. Okay? Like this, basically. And what we want to do is we're just going to define this. Okay? Use the letter E, and that's the coefficient of restitution. Now, in kinetic energy conservation, okay, these two are equal to each other, so the ratio is 1, okay? And if you have inelastic or perfectly inelastic collisions, then it's going to be less than 1. But let's go back to, why don't you go back to the very beginning to that scale that we set up, okay, on the very first screen, and you'll see what's going to happen here, okay, is that on this spectrum, okay, on the far right, the coefficient of restitution will be 1 if it's an elastic collision. And then here in the middle, you're going to have less than 1. But the neat part is that in a perfectly inelastic collision, right, the objects move together after the collision. So their speed relative to one another afterwards is 0. And so you have a way to cap the left end of the spectrum, so to speak, right? If you just look at kinetic energy, it's just much, much less. But in a perfect inelastic collision, you actually have a coefficient of restitution of 0. All right, there is collisions in a nutshell.